Okay, so we have been talking about many gradient descent method algorithms. Okay, so basically in machine learning, when we estimate parameters, there are a couple of different approaches. First, if the problem is really simple, then the closed form solution would be possible. When the closed form solution is not possible, then we can think of iterative update rules. So gradient descent method is based on this iterative update. And iterative update means we need initializations. Okay, so we have to initialize the parameters and then we can iteratively update the parameter from there. So the question is, what kind of initialization is better than the others? Okay, so basically we use random initialization. And then the real question is what kind of distribution we are going to use to select random initialization. Okay, so if the Gaussian is the distribution, and then given the layer, okay, so X is a lower layer and the Z is the upper layer, but right before the activation function in the neural network, then we have this equation. And when we have variance of xy, this is actually variance of x times variance of y if they are independent. Okay, so if we assume this, then we can have this one. So if we assume this one. So in this equation, so we don't want to change this variance. Okay, so in the neural network, so this one has a variance, and then this one has a variance, but we don't want to change. If we change the variance, then it's not a good idea, because if the variance of this is bigger than this, then when we have a small change in this layer, then we're going to have a big change here. So that is kind of unstable solution. So we want to just keep the variance. So this one and this one should be the same. That's our kind of hope. And then the variance of W should be like this. And then if the input layer and the output layer, if they have different kind of dimension, then we can take the harmonic mean of these two. So the variance of W, the element of W, should be something like this. And this is a Xavier initialization. The Xavier initialization from the Gaussian distribution is really popular, so you can use that. But there's one tiny little problem with the Gaussian distribution. Look at this one. This one is Gaussian distribution, and this one is a uniform distribution. So when we initialize the parameters from this Gaussian distribution, then probably all the parameters are around here. Okay, that's okay. But there is some possibility to have a really large value. Okay, even though the probability is small, but still there is a probability, and we can have a really small number with a small probability, but it's possible. So if we have this kind of value to initialize the parameters, then that makes the training process hard. Okay, but if we use uniform distribution, then it's safe. It's safe in this regard. Okay, so we cannot get any too large number here. So all the random values are from this range for sure. Okay, so let's initialize the parameters with uniform distribution, but we want to keep the same kind of principle. So we don't want to change the variance. If we select initialize the parameter from the uniform distribution from minus s to s, okay, this is the range of this uniform distribution, and then the variance of this parameter will be s squared divided by 3. So this is the variance. And as you know from the previous slide, we have the same equation. So this one, the variance of z should be the same as this one. So this one should be a 1. So the variance of wij should be 1 over nk plus 1. Then s squared should be 3 over nk plus 1. Okay. And then when the input and the output dimensions are different, then we can use the harmonic mean of this one and this one. So now we have this one. Okay, so since s squared should be this one, then we have the uniform distribution for the parameter initialization. So this one is a Savary uniform initialization. I think this is one of the most popular initialization technique. Okay, but there are a couple of questions that you have to think about. First, what if the input is always positive by ReLU? Okay, then we don't have negative input. Always we have positive. That changes the distribution of the input. Then the parameter should be from a little different distribution. Okay, so we have to think about that. Actually, when we use ReLU, then the here initialization is a little better. But when you use a couple of different initialization in your experiment, usually many times you cannot tell the difference. They are quite similar, but sometimes one specific initialization will be better than the other. Okay. Also, what if half of them are dropped by dropout? Then we can think of a modification of this initialization. Okay, so anyway, this is the basic kind of Savary uniform initialization. And another one is parallelized learning. Basically, there are two different parallelization. First one is model parallelization, and the second one is data parallelization. So the model parallelization is not as simple. So to use this model parallelization, we have to implement a learning algorithm in a different way. So it's not the simple approach. For example, AlexNet used model parallelization, and Google NMT neural machine translation used model parallelization. So in AlexNet, back then the GPU was not that computationally powerful. So given this image, then he actually used the two GPU. So there are two paths. So this one is GPU 1 and this one is GPU 2. And then they combine and classify here. But it's not just the separate processing. So sometimes they have passing some information between these two GPUs. So what I'm saying is that in the model parallelization, we split the model, and then each computation unit can process some part of this model, and another part can be done by another computational unit. Okay, so and then in the Google NMT, in the NMT there were a lot of layers. This one was 2016. This one is 2012, I guess. So in 2016, they used many RNN layers. Okay, so when they have 8 layers for the encoder, then each layer was done by one GPU. So they used 8 GPUs to process this encoder architecture. And for decoder architecture, there are 8 layers, and they used 8 GPUs for the decoder. So they used 16 GPUs to process this architecture. Okay, so if you have many computational units, and then if you want really large network architecture, then maybe you might have to think about this model parallelization, but it's really complicated. But most of the time, data parallelization is the parallelization that we use, because this is really simple. First, we distribute the data samples to the slaves. So we have many slaves servers, okay? And then we distribute the data samples like this. It's kind of subset of the data set. And then from this master, we have a model, and then we copy all the models. And from this server, we update the parameters. We update the model with this data. And in this server, we update the model with this data, etc. And then we update these parameters for a couple of iterations, and then we pass this one. We can pass the whole model, or we can pass the delta, okay? And then in the master server, we can combine all these updates, or we can take the average of all the models, okay? And then we copy this one again to all the slaves, and then we update models here in slaves, and then we integrate again. So we repeat this process. This is a basic idea of data parallelization. So when you have many GPUs with many servers, then this could be quite efficient. And another one is kind of old-fashioned idea. We can decay the learning rate. So let's say this one is training loss, and training loss could go down. It decreases, and then if you don't have any techniques, then it goes something like this. But we can reduce the learning rate at this moment, then all of a sudden it goes down abruptly. So it's not easy to explain this phenomena, but it happens when the learning rate is 0.01. So we train for a while, and then when you feel the update is not large enough, then we drop this learning rate from 0.01 to 0.005. Okay, then training loss decreases abruptly. Then you will see this kind of phenomena a lot. Okay, but do not reduce the learning rate too soon. Okay, so if you do that, then you will see this kind of cross. So you have to wait until the training is enough. And then the last one is regularization. So we have a lot of different types of regularizations. Then we'll talk about this one in the regularization chapter.